morning. Here we are once again. It's the physics video lecture. Physics 2A video lecture 40. Moving right along. Okay, we have an interesting topic today that spans both chapters 11 and 12, or two topics. And it's right where we left off. We're talking about heat transfer mechanisms, heat transfer by electromagnetic radiation. So let's look at these things, and then we'll get an interesting application. Well, first of all, when we're talking about heat transfer, I'd like to start with our cartoon, that we have some higher temperature, some lower temperature object, and the energy flows from hot to cold. Okay? And then those three mechanisms are conduction, convection, radiation. So I'll write them down. Conduction, molecular collisions. So you have to actually have some matter there. Convection is fluid flow, air, liquid, water as well. Fluid flow and radiation. And this was electromagnetic waves. And the all-time great example of that is our sun. And so what we're going to do is talk about solar radiation and figure out how much there is, how powerful it is, that kind of thing. So radiation was electromagnetic waves. And our sun sends us its radiation across millions of kilometers, hundreds of millions of kilometers of empty space, of vacuum. So it's not conduction or convection that's bringing that energy to us. So electromagnetic waves. And therefore our next topic is solar energy, solar radiation. And we want to know how much. How much energy is flooding us when we stand out in the sun, for instance. Seems like there's more in the summer than in the winter, but we'll see about that. Okay. So what I'm going to do is describe an experiment that we could do ourselves, although these things are easier to describe than to do. But we're going to talk about measuring the intensity of the solar radiation, okay, the solar radiation. How much is there? And so I have to draw a picture of, and here's the time for some colors. Okay, so we're going to have our incoming sunlight, and we're going to have it strike a box with a transparent surface. So I can draw some perspective here. Wish me luck. Okay, there we go. So this is a surface area A that is facing the sun. And we're going to want this to be very dark. And the box is filled with water. So there's water inside. And that perspective isn't that good, but you get the idea. Sunlight. Some surface area A, I'll write here. Area A, that's how the sun gets into the box, and what it's doing is it's heating the water. Okay. So it's heating the water, and what we'll do is we'll draw a little thermometer here. And got the old, okay, there's a thermometer, degrees Celsius. So we know we're measuring the temperature of the water. The temperature of the water increases in time because it's under the sun. And in fact, you've seen this and felt it in the summer. If you have a hose out there in the sun and you turn the water on, then some hot water comes shooting out of the hose because it's been laying in the sun gathering energy. So that's a basic experiment. we have a surface area A here, and we have, so I'll write these down, area A, mass M of water, and then the thermometer measures the increase in temperature. Increase in temperature delta T, oops, let's call that capital T, delta temperature, and it's increasing in time, in the time delta T. Okay, so we can use those data to figure out the amount of energy flux. So first of all, we're just going to do this in a few steps. If we're heating up water, we know that we have Q equal to mc delta T, right? That's the energy in joules, mass of water, specific heat of water, change in temperature in degrees Celsius. So power, just number these. Actually, how about this? How about this? We'll do a several step little operation here. So the first step, we talk about energy, and Q is mc delta T, just as stated. Okay. So the next step, we talk about power. P is equal to, let's go ahead and call this delta Q. Makes no difference, right? That's an increment of heat. So P is this delta Q divided by delta T. And that's mc delta temperature over delta time. So that's energy. We know about energy, that's power. Now the third concept here, that's a new one, it's power per area, power per meter squared, and that's intensity. The units here we already know, right? This is joules, this is watts. So the intensity, I is equal to P divided by area. It's just going to be watts per square meter. I'll even put this right under here. Units, it's going to be watts per square meter. And when you think about it, that's what we're interested in. If we have so much sunlight falling on this table, measure the square meters, figure out the total watts. Good. So watts per square meter. So our formula here is mc over A delta T over delta T. Now this formula is actually just a description for our experiment. The definition of the intensity is power per area. And this is for the particular experiment we're doing, which was sunlight's coming in, there's the area of that box, the mass of water inside we measured. Maybe we put a bunch of ink in the water to make it totally black so it would absorb all the heat, for instance. Okay. And then specific heat of water, we know change in temperature over change in time, so we have to do an experiment and track the temperature and the time. Okay. So we have a watch so we can measure the time. So let's have a look at what that would look like if we were to do it. Again, much easier to talk about it than to actually do this, but I think the concept is pretty clear. So let's go ahead and have a look at that. So what I'll put up is a graph. The idea is we'll put it right under here. And this is temperature versus time. So T in seconds, temperature in degrees Celsius. Temperature versus time, and I'll put here parenthetically water under the sun. Okay. So what are we going to find? Well, the water temperature, suppose it starts at room temperature, 20 degrees Celsius, and now I'm just going to make up some numbers. What's going to happen is the water is going to increase in temperature, but it's not going to increase in temperature forever. Eventually, it's out in the sun, it'll reach some high temperature, depending on how hot it is and how efficiently we gather all the sunlight. So it's going to reach some saturation value, and so we do this experiment and we get a curve here. Well, of what use is this curve to us? We're looking for delta T temperature over delta T time. And so what we could do is take the maximum slope of this curve. Okay. So we measure the slope, got another color here. Okay. And the slope would give us that thing that we were looking for before it reached its maximum temperature. So slope equals delta T over delta time maximum, all right? And what do you know? We will now have filled in everything in here, and we await what is that number. Okay? That number will tell us how many watts per square meter of sunlight are coming in at us. Maybe at noon would be the best time to do it on a clear day. Okay. So the result is referred to as the solar constant. And I'm going to give you the official number, the ideal number. So it's on the order, it's 1,340. If you look it up, it says 1,340, 1,360 watts per square meter. I'm using 40 here. And this is the value you would get if you did this experiment carefully above Earth's atmosphere. So there's no atmosphere, let alone any clouds or anything else to reflect the sun away. So this is the maximum value. This is the solar constant above the atmosphere. Down here at noon, let's just say we would find roughly 1,000, which is actually a nice number to find, right? So this is above the atmosphere. At the surface of Earth, I'll just write I is more like 1,000. For our purposes, we can just say 1,000. Good number. Okay. Watts per square meter. So this is the number that you can start all of your solar energy calculations with. 1,000 watts per meter squared. That means the sky is completely clear, the sun's coming down perpendicular onto your surface there. If the sun is lower in the sky, then you have to tilt your surface up to meet it. Okay, so if the sun's direct, I'll use this physics book right here. This folder's better. Okay. So if the sun is directly overhead, then we want to face it like that. If the sun's coming in at an angle, then we actually have to tilt it this way in order to get the full solar energy, the full solar flux. If it were flat here, you could see it only be getting cosine of that angle. So you want to be perpendicular at all times. Okay, we could say that's understood. Solar constant. there you have it. Okay, so like I said, you begin all of your calculations with this. Then you have to say, well, what about night? If I want to run this all day, then I'm not going to be getting 1,000 watts all day. So you have to start cutting that down based on how many hours of sunlight you have. Then, if you're doing it over a day or a week or a month, you have to factor in that not every day is perfect and cloud-free. Of course, you factor in day and night. And after that, if you're actually gathering this energy to use, then you have to know the efficiency of your system. Okay. So this number, which is, fantastic, a lot of energy, a lot of power per square meter, is then in practical situations cut down by so and so many percent. Nonetheless, this is what we have to work with. Okay, and you see, it's a nice conceptual thing because we've studied all these things now, and we needed what we have we needed the radiation, and then we needed specific heat capacity and concept of power and so forth, and we have this new concept of intensity. Okay, so that was the one topic I wanted to talk about. When we go into the next chapter, we're going to return to it at the end of the chapter, but for now, we know how much. So let me consult the clock here and see what's next. Fantastic. The solar constant. Actually, let me add a little bit to that before we move on. So underneath this solar constant concept, we can do some conversions. And we'll use the same letter so the 1,000 is good. Now we're going to talk about average values. So suppose we start with 1,000 watts per square meter. That's what we start with. But then we say the sun is only shining at full strength for some fraction of those hours per day. So how many hours do we have sun at full strength? That would be seasonal. Here, let's put a vocabulary here. Insolation, not insulation, but insolation. S-O-L refers to the sun. So we've got 1,000 watts per square meter equals 1 kilowatt per square meter. Okay. Now we could say we have 24 hours per day. So I've actually multiplied this equation by 1. This is a 1 because it's just hours and days, right? Both time over time. So what we're looking at here is 24 kilowatt hours per meter squared per day. That's another way to look at the solar energy coming in. Of course, do we actually have 24 kilowatt hours per meter squared per day? Well, we don't have 24 hours of sunlight. So this is where I'm saying we have to measure during the, we have to take an average over day and night, cloudy and clear days and so forth and so on. And then we get this example. So let's put, good, so this is actually just an identity, so we're fine. So now, as an example, if we incorporate day and night, sunny versus cloudy, etc., whatever conditions you have, raining and so forth, then we might find I is equal to 1/4 of this. Okay, half the time the sun's not up, and the other half, and half of that, it's not as, it's not fully sunny. So if we had 1/4 of that, so multiply times 1/4, then we would have 6 kilowatt hours per meter squared per day. Now you can find maps, and if you look this up online, you can find maps where they give the amount of insolation in this form, and you'll find maps where it's 6 kilowatt hours per day, and the maps may even incorporate the seasons, and they'll say, more in the summer, less in the winter. But this is a number you can use, and this type of number, depending on where you are, to plan large-scale and long-term solar energy. Because then you would say, well, I'm getting, on average averaged over the year or the month, whatever, I'm getting 6 kilowatt hours per square meter per day. And then you would have to take this number and find out how much efficiency you have in your system, and then you would knock it down by some percentage as well, which we can get to later. But for example, solar cells, the kind people have on their roof nowadays, photovoltaic cells, will be maybe 20% efficient. So you would take this and divide it by 5, okay, 1/5. And over the course of the year, that's how much energy in kilowatt hours you would get per square meter of solar panels. So just with these basics, you know more than almost anyone else out there. And the solar panel salesperson is going to have to look this stuff up on a spreadsheet. But armed with this knowledge, you guys could just work it out with a pencil and paper, okay? And then you can compare. Good. So that's a nice little section on solar energy. We'll return to this later on in the next chapter, but at this point, that's a good set of notes. Okay, great. So that's the one topic I wanted to cover. Our next topic is back again to heat transfer. And we'll just look at the conduction and then take a closer look at what's going on. And we're gonna jump right into chapter 12 of this. But returning to heat transfer. So next, heat transfer once again. May as well always use our cartoon. In fact, this time it's going to be truly important. The thermal energy is going from the hotter to the colder. That's an H. Okay. And we'll consider conduction. And we'll do a close-up look at that demonstration. We've got our torch. Lacking a torch, we've got a butter candle. Flame. Okay. And we have that aluminum bar. And the question is, what's going on when of course we feel that the heat is transferred in this direction, because we can grab it at any point and eventually it'll get hot. Okay. So the heat is definitely going in this direction here. I can kind of indicate it as a wave like that. Heat's traveling from hot to cold, cold end. But what's going on microscopically? What's going on if we think of this metal bar as being composed of atoms, molecules? Okay. So what's going on there reminded of our theory of the ideal gas. What's going on is these particles are in random motion and they're moving faster when they're heated, right? They're agitated. And when I said molecular collisions for the conduction, I meant that these things that are moving faster are colliding with the ones that are moving slower and therefore kicking them into action. So that's the idea of, so when I say microscopically, I've returned to molecular collisions. Which we've heard before, we're just addressing it again. Molecular collisions, so these things are faster, molecules are faster, and over here they're slower. And so that's what it means on the microscopic level, for the energy to go from one object to the other. Okay. So this idea generalizes to the idea that where they're faster, it's disorder. And where they're slower, it's order. And we have disorder because they're bouncing every which way. We have order when they're just frozen into place. And then you could say, okay, a piece of ice represents order and gas molecules represent disorder. So let's send this up here and give these examples. So the order and disorder corresponds to the slower and the faster molecules, and the direction of the heat flow corresponds to the order turning to disorder, okay, as the temperature flows in there, as the energy flows in there. So I'll do these other couple of examples. And in fact, when we did the phase change, that was the perfect example for order and disorder. So disorder and order. We'll go to the phase change. Once again, remember we had the ice, and then we had the water, the fluid, solid, actually I should say the solid, the fluid, and then we had the gas, and I drew a balloon or something, okay? And we were adding energy. So what we're seeing here is we're going from order to disorder. Order, disorder, even more disorder. And this disorder is seen explicitly on the molecular scale. If you're just looking at the ice and the water, you're not really seeing order and disorder, but if you see them as being composed of molecules moving around, then you see it. And so we get a concept called entropy, which is a measure of the disorder. Now there's an expression for the entropy that really does talk about it on the molecular level, but we're going to talk about it on the macroscopic level as a measure of disorder. And our expression for it, we're always going to use a delta for it, okay? Change of entropy. Our expression for that is a quantum of energy divided by a temperature. So the units are joules per Kelvin. This temperature has to be measured in Kelvin. And this is the change of entropy. And it's the change of entropy when energy flows, when thermal energy flows. So change of entropy during or due to energy flow. thermal energy flow. So there's our formula. This is in the back of chapter 12, but as usual, my way is the best way, and it's best to talk about it right here, because the real example is the heat transfer. The best example is the heat transfer, and of course the phase change is a good example as well. So what are we going to do with this? First of all, I'm going to show that this definition, I'll add a bit to the definition, is the equivalent of this cartoon up here. And then later we'll use it when we analyze the heat engine. Okay. So I have a few things to do with this. Let's see how we're doing time-wise. Perfect. We've got nothing but time. So entropy is a measure of the disorder, and I have to be a little more specific now with what this means. So let's open up another board. Like I said, in the book you'll find this towards the end of chapter 12. Okay, so let's do this change of entropy and the rules that go with its calculation. So once again, what I just had up there, delta S Q over T, and we're looking at Q into an object of temperature T. So say energy is flowing into something. Now I have to be a little more specific. If Q is positive, then delta S is positive. Okay, if Q is positive. So in other words, if energy is flowing in, then delta S is positive. If Q is negative, right, energy flowing out, then delta S is negative. Okay. And what we want to do now is talk about the change of entropy in a closed system. So the other thing is the total change of entropy would be if you add up all the individual changes of entropy. So this is, I'm just going to number these little things here, 1, 2, and 3. Delta S total is the sum of all the delta S individual ones. Okay. So next we want to look at delta S total for a closed system. And the closed system is this one. Where's our cartoon? Same old cartoon. T, H, Q, T, C. Energy flowing from hot to cold. But what we're going to do is put it in a cooler. We imagine it's a closed system. So this is all that's happening. So there are two little changes of entropy because we have these two objects that have contact with each other. You know, we could throw a whole handful of them in there and then it would be more complicated, but we just have these two. So this calculation is key because for the closed system, let's put a couple more words here. Closed system with, you know, TH and TC. So in practical terms, this is a cooler, and you threw in something hot, something cold. Okay, and then you wait a little bit. It's closed. Close the lid. Okay, so let's calculate this. My closed system. My definition up there, so we're ready to go. Yeah, so this seems really formal, but the delta S total is going to be delta S, I'll call it H, plus delta SC for these two processes. In other words, some Q leaves TH and it enters TC. So what do we have here? We have the one for leaving, it's minus absolute value of Q over TH. Okay, that's the rule. Energy's flowing out, negative, and it's plus the Q over TC because it's flowing in. Okay. So that's the simplest entropy calculation for a system. And let's see what happens with this basic scenario. We have delta S total equals, we can pull out the Q, which is a positive number, then I have 1 over TC minus 1 over TH. And to make it more explicit, I can get a common denominator, and I have TH minus TC over TC TH. Okay. So we could look at either one of these. I'll put a box around this one. And we get a fundamental result. Because higher temperature minus a lower temperature is positive, and Kelvin temperatures are always positive. So what we have here is this is always greater than 0, or we could say greater than or equal to 0. And it turns out this is a law of nature. Delta S total for an isolated system is always greater than or equal to 0. So the entropy is always increasing in an isolated system. And the reason we can believe this or accept this is because what is it based on? It's based on energy flowing from hot to cold, which is something we do not see violated. Okay, so this entropy law, which I'm about to formulate, is equivalent to energy flowing from hot to cold. And it's called the second law of thermodynamics. That's funny. I'm doing the second law of thermodynamics. Haven't done the first law yet. Okay. We'll see. You have. Second law of thermodynamics. And that is that the entropy of an isolated system is always increasing, or at best unchanged. Okay. So the entropy of an isolated system increases. And we'll just leave the understanding that the best case is that it would remain constant. If an isolated system increases, then that's delta S total greater than or equal to 0. Okay. Yeah, what about the first law? It's not that I'm doing this backwards. The first law is really just conservation of energy. And we've talked about conservation of energy a lot, but that doesn't mean we're done with it, because we had conservation of mechanical energy, and we had problems with friction and talking about energy there. The first law just includes all of the heat transfers and other dissipation events that happen due to friction, collisions, and other things. In other words, the first law of thermodynamics includes thermal energy. So if you include thermal energy and all other chemical energies and electrical and everything, then energy is neither created nor destroyed. Okay? It's always constant. Constant means conservation. So we'll return to that a bit. So we've talked about the first law. We're not done with it. The second law, though, has to do with the direction that energy flows, and it always flows from hot to cold. It moves to increase the disorder. That's what we started with this thing here. And this is the proof in terms of just the very simple system, energy flowing from hot to cold, namely that this expression is always positive, okay? Positive, and actually, when TH equals TC, in other words, if you wait long enough, then the entropy will reach a constant value, but until that happens, it's always increasing. Because if you wait long enough, TH and TC are the same. Okay. The only thing I'm going to do now is put a couple numbers in. And then we'll be good to go. So I do want to do a little calculation just to show this, and then I'll assign a couple problems that you guys can practice that. It's pretty theoretical stuff, but we've got a whole semester, we've got the background to understand these things. So let's do it. I'm going to calculate an example. Ice at T equals 0 degrees Celsius melts to water at T equals 0 degrees Celsius. So that's classically order to disorder, okay? And the change of entropy for this process is equal to Q over T. But that Q is mass of water times the latent heat of fusion of water. Okay, remember we had mass, we had latent heat of fusion, so that's Q. And the temperature is going to be, I'm just going to do an arrow here. This is going to have to be 273 Kelvin. Okay. You're not allowed to put degrees Celsius in here. That'd be the 273 Kelvin. So you put those numbers in, and then you get the actual change of entropy. Okay, I'm going to consult the book and see if we have a couple good problems to do. There may be another solar energy problem from chapter 11. And if we did it already, I'll just recommend it. Well, we did talk about 71, but here's a good homework problem. So homework number 40. This one you'll enjoy. It's problem number 67, chapter 11, problem number 67. And they give 960 watts per square meter for the average Earth's surface solar constant. So that's pretty close to the 1,000 we talked about, 960. Very good. Okay, you'll enjoy that one. It's about the Earth receiving solar energy and radiating an equal amount away according to Stephan's law. Okay, that's good. Chapter 12. We really just want to plug a couple things in here. We're at the very end of chapter 12, which is fine. Let's see if they have anything for us. Good, so we're doing chapter 12, 48. That's basically what I just did right here, so that's a good start. I'm going to say 48 and 49. They're really the same problem, okay? Different numbers. And 53. Good. And of course, if you're interested in these, I can do them in a lecture. Just let me know. But there we have it. Very good. So we're through chapter 11, and we already jumped to the end of chapter 12. But chapter 12 will have a lot of great stuff as well. See you guys next time.